want to answer. So that's what I want to answer, that it is possible to verify. It is possible to verify up to an extent. But how do we do that? So there's lots of mathematics and some astronomy we should go around over here. Got some props. I hope you all would enjoy the talk. Let's just see one more thing.
He has a lot of fun with me, so you get to find it out very stuff. He's also an all-around English, so he's given a couple of talks right here and before he's in the topic. So he's not going to all of this. So feel free to ask him all the questions that you have. Feel free to question him. And of course, you know, it's a lot of talk. That's part of the channel.
Is the topic of this?
We will be announcing it shortly. We will be announcing it shortly. How many are coming here for the first time? How many this is the first time? So, Chai is something that the outreach committee takes part into, and this is an event which happens every odd Sunday. So, the first Sunday it happens in Prithvi Theatre.
The third Sunday, like today, it's happening here in Duparel. And if there's a fifth Sunday, so not every month would have a fifth Sunday. If there is a fifth Sunday, then it would happen in Alexandra School in Fort. So the next Chai and Wai, if I'm not wrong, they have announced it. I don't have the slides for the announcements, but you can have a look at the Chai and Wai Facebook page. So the Chai and Wai Facebook page, it has the announcement. It was announced 2 or 3 days ago, if I'm not wrong. The next Chai and Wai, it has been announced. The next Chai and Wai would be in Prithvi Theatre.
No, that's fine.
Yeah.
I was just wanting to know the subject.
Yeah.
The speaker and the subject will be declared shortly.
Okay.
Since Annapurna Kulkarni are busy for a while.
Okay. Okay. So let me start this Chai and Wai by firstly thanking you all for coming on a leisurely Sunday. I myself don't like to wake up on Sundays. Okay, so is it the year 2020? So, I mean, I'm asking a question. The title of this talk is a question. Is it the year 2020? So, this question might not make sense to us because all of us walk around with these devices which control our lives. I suppose all of you have this device. We call these devices lots of names. Some people live with their devices day and night, even take baths with that. But these devices give us time, date, and everything. And they actually keep on giving us more accurate definitions of time. So how many of you know that this device, a mobile, a cell phone, is actually related to a satellite which would keep on giving you new data regarding your time scale? So there's proper time changes which happen because of GMT. That gets accentuated into this. Now all of this is happening without us knowing or without us just practically knowing it. But if I ask you, what is a year? Without knowing this device, can you answer that question? What is a year? Okay, wait for a few moments. I'll actually show you a slide where you have to answer me, okay? So, I suppose all of you like some stories. How many of you have heard of the mad scientist paradox? The story of the mad scientist. Time travel stories? Have you heard of the mad scientist paradox? Okay, so I'll tell you very simple. Huh?
You kill your own father how you want?
No, he kills himself. So he is a mad scientist. Unlike me, he's a scientist, okay? So he makes a time machine. He goes back in time with a gun. He goes to himself before he makes a time machine and shoots himself. So he never made the time machine. So he never went back in time. And so he never actually shot himself. Then what did he do? So whenever we're talking about time travel, such logical paradoxes keep on happening, which question causality. That if you actually go and kill back the cause of yourself. So there's something similar called as the grandfather's paradox. Go back in time and kill your own grandfather. Then you won't exist. So quite simple like that. But okay, I want to change the story a bit. So instead of the mad scientist story, let's go to the forgetful scientist. So the forgetful scientist, as the name suggests, he's forgetful. So he again makes a time machine. But now what he does is, after making the time machine, he forgets to check everything. So he goes, he starts his time machine, and the time machine is like a car, and the dashboard for the time machine breaks him. The wires were loose maybe, he was forgetful. So now he's gone in time, maybe forward, maybe backward, he doesn't know. What he knew is that he had enough fuel to at most take a leap of 5,000 years. Maybe in the past, maybe in the future. Now he suddenly opens his time machine and he's like, oh shit, I don't know where I am. He looks outside and a new civilization is there. They have a different language. Maybe he's gone to the Mayan civilization, maybe he's gone to Egyptian, maybe he's gone to some place in future. He doesn't know what year it is. Now he has to go back. So he'll have to punch in exactly, I mean, even if he corrects his time machine, he has to punch in exactly that many number of years that he has to go back in the past or in the future. How will he know? How will he know what year it is? Let me rephrase my question. Is it possible for him to know that which year it is in the calendar system? Is the calendar system robust enough to tell us what year it is without actually looking at a device like this? Can I make an observation on the outside world to know the year? Now we can say what the day is just by looking at the type of weather, maybe where the sun is and things like that. Looking at the stars, we can tell the day in a year. But can you tell me the year itself? Is it possible? That's the first question which I want to ask over here. So keep this question in mind. Can you predict what year it is based on external observations? For most things on Earth, you can't. That's a very simple answer. If you're looking at the things which happen on Earth, you can never answer that question, because most things which happen on Earth, they're happening periodically, and the period is mostly related to either the period of moon or the period of sun. But nowhere would you actually find something which is relating the period of this revolutions. So how do we answer that question? Okay? And again a question, can we actually answer that? Can he go back? So we'll come back to this later, but okay. What is a year? You had an answer for me, right?
Like a year is a period of time which covers 12 months, 52 weeks.
Okay, so I'll give you some options. Okay, I have some options over here. Which one of them would best define a year? So I have 365 days. I have 354 days. I have 365.25 days. 365.2425 days. And 365.24219 days.
365 or 95 days.
0.25 days. This one? So you're saying that there would be 365 days, which is 12 months, plus a leap year every 4th year. Yes? Agreed? Everyone agrees with him that this is the definition for a year. The last one? So you're saying this one is the year? Anyone else? So let's take some votes over here. How many say it's 365 days? Anyone who says 365 days? Okay. 354 days. No one for 354 days? Fine. I'm for 354 days. Okay. 2 over here for 354 days. 365.25. So the young gentleman over here. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 8 people for 365.25 days. 365.2425. Anyone going with this? Okay. I have got 3 here. Last one, so you were there, right? Okay, so I have got 1, 2, 3, 4, 5. 5 people who say 365.24219 days. Do these appear like random numbers? Somewhere I just got a random number generator and made some decimal expansion with 365, something like that? Which one do you think should be the correct one? 365.25. That is it. All of them are correct. All of them are actually years. So when I say a year, it has to be a very specific year. So 365 corresponds with the Egyptian year. So if you're looking at the Egyptian calendar, their year. So year is a time period. Firstly, get that notion in picture. Whenever you're saying a year, an year is a time period. You can't say that an year is exactly some period of time. If I'm saying an academic year, if you're a student, academic year means 12 months. If I'm saying an astronomical year, it means something. If I'm saying a solar year, it means something. If I'm saying a Gregorian year, it means something. So all of these are different years. So if you're looking at an Islamic calendar, their year is exactly 354 days. That's a lunar year. If you're looking at the Julian calendar, which was in prevalence for a very long time, in which every 4th year is a leap year, then it would be 365.25 days, as the young gentleman over here said. But we don't follow the Julian calendar anymore. The calendar that we follow is the Gregorian calendar. And this calendar says that every year is 365.2425 days. But the mean tropical year, the one thing that we're trying to approximate, is the solar year, 365.24219 days. So, okay, one more thing. When I'm saying a day, what is a day? Okay, let's not make any confusions over here. A day for me is exactly 24 hours, where each hour is 3600 seconds, SI seconds, where a second is some vibrations of the cesium-168 atom for me. Okay, so that definition I have just put in picture that, okay, I have defined a day for myself. Now, using that standard, I'm looking at years. Even days can have different meaning, by the way. So if you are going into astronomy or you're looking at astrological days, then there would be things called as sidereal days, solar day, and things like that. I'll come to that later. But that goes on in calculation for many other things. Okay. So all of these are years. So which year should we consider? Gregorian year? You think so? So if you were just someone who's looking at things, maybe going to school, you want to know which days are holidays and things like that, Gregorian year is the best.
No, it's academic year.
No. Academic year is Gregorian year. So the academic year that you have is based on Gregorian year. So this Gregorian year cycle, that is what we call as the standard for civilians. There are other years as well. So if you're an astronomer, if you're someone who's doing some calculations over there, you would always consider this or the sidereal year. Okay.
What's the difference between the Gregorian and the previous one?
So the Gregorian and the Julian?
What's the difference? How do you calculate the difference?
So I'll come to that. There is a huge difference, and this difference is what led to the whole change, and this was a huge reform. So there were only a few times in our history when actually we had to just take a leap of few days in the calendar, and that was when the Gregorian reform happened, and I'll come to that, and that's one of the most interesting parts of this talk. Okay, so the history of timekeeping. Now, how do we keep time? Before that, what is time? Anyone who can answer me what is time? Answered like a physicist. Okay, so this is the Wikipedia definition, which I hate. Okay, so it just says time is this indefinite, continuous process which is taking things from past to present to future. Okay, we have an idea about that, but you know what definition I like? I know what time is as long as no one asks me what it is. But the definition which most physicists would agree with is this. Time is something which a clock reads. Now we are not defining a clock. A clock can be anything periodic. The motion of sun, it's periodic. We are saying that it takes a day for sun to just take one round over here. Well, it's actually a round of Earth. I mean, Earth is rotating over there, and that rotation is what's creating a day for us. That's a periodic motion. Along with that, we are seeing another periodic motion, which is the seasonal cycle. Along with that, we are seeing the seasonal. Along with that, we are seeing the tidal motions. So we are seeing lots of various phenomena in which there's periodicity. And this periodicity, this recurrence tells us that, okay, so today sun started in the east. Tomorrow would it start in the west? No. We are pretty certain it wouldn't. Why? Can anyone tell me why it won't happen? Can anyone guarantee that?
I think because the Earth spins anti-clockwise, so the
You are not getting, we know that fact that yes, Earth is revolving around the sun while Earth is rotating around its own axis. But can you guarantee that this would happen always? So we can just say that based on current physics, yes, it should happen. But well, we don't know what might happen later. So we are assuming that physics is true. So in this whole talk, we are gonna believe that physics is true. There's no magic happening, no Willy Wonka and the magic stick coming out from anywhere. So mostly it's just based on some physics and astronomical data that we'll be using over here. So I'll be introducing lots of astronomical phenomena in between, and I hope you all keep up with me. And I would try to correlate with that with some of the Indian words used over here. So let's move forward. So I will assume that all of you know what time is. I won't ask you what it is. You all know what time is? Everyone knows what time is. So humans at the age of something like 3 or 4 are able to recognize passage of time. There was a psychological experiment done like that. Kids were asked that, okay, fine, I'll give you 1 chocolate now. If you can keep it for 10 minutes, I'll give you 2 chocolates. So knowing that, okay, after some passage of time, is this passage of time valid enough for me or good enough for me to give away this chocolate to gain 2? So by the age of 3, kids can do that. Before that, they'll eat the chocolate. Okay? So this is a simple experiment to say that time is something which we inherently come to understand by the age of 3. So for most reasons, I'll assume that everyone knows what time is. But where did we started knowing about how passage of time is going on? And why did we need that? So the first evidence that we have of people knowing about long passages of time have been before 10,000 BC. That is the Neolithic age, which we call as the New Stone Age. So at that time, they have had longer periods of time, like calendars in picture. Now, I assume many of the people over here have had a look at any documentary on Stonehenge. Have seen what the Stonehenge is, okay? It's somewhere in Wales or something like that. It's a huge thing made up of tons of stone, some 31 stones and some 71 stones like that put in some picture. But they believe that the Stonehenge was also a timekeeping place. And it's almost something like 1500 years old, 15,000 years old if I'm not wrong. So it's even before it's in the Paleolithic age. So we have been having long passages of time being recorded. So Stonehenge is said to be something which recorded the passage of time in a year. There have been other calendars like the Sumerian calendar, which is supposedly 20,000 years old. So passage of time is something which we have been looking at, and what we just want to observe is this periodicity and be able to predict what's happening over there, this heavenly Tao. I mean, there's lots of stars, there's planets, there's sun, there's moon. How are these moving about? Can we predict that? So that was the major question which people tried to answer. That's when timekeeping started. And the reason for that is, well, we needed to know things. I mean, we as early humans saw that there's this whole world made for us. There's this night sky. There's the sky in which there's this hot yellow disk moving about. Okay. There's this white disk also, which sometimes is large, sometimes is small. Sometimes on the white disk you see that there's a rabbit, or sometimes there's a grandmother's face over there. Okay. And along with that, whenever this yellow disk goes down, you would see that there's some twinkling lights again. So we named these things, and we saw that these are all very periodic in nature. This yellow disk, this would come up and go down every day. The white disk, not something like that. It would be a bit less than a day. So what is the name of the yellow disk?
The sun.
White disk? And the lights?
Stars.
Exactly. So this is something which we all know now. This is not something which people long back knew. So I'm talking about the early ages, 10,000 BC. Okay, so what we saw is that, what we named at that is this one day is the time period which sun or this yellow disk took to come and go. And 29.5 days was approximately the time that the white disk, moon, took to revolve once. Okay, that is all the phases. So whenever I'm saying this 29.5 days, it counts the phases of the moon. So from one full moon to another full moon, the amount of time taken is 29.5 days. Is it equal to the amount taken by moon to revolve around Earth? Yes? So the amount of time taken by moon to revolve once around Earth is the same as the amount of time taken for moon to go from one full moon to another full moon. How many agree? Okay, you're wrong. So the amount of time taken by moon to revolve once is 27.3 days. 27.3 days. So this difference, I mean, this is called a sidereal lunar month. So I'll talk about sidereal days. I mean, that is, how many here know about Kundlis, Tithis, Varnas and all that? So Tithi is something which is there. Tithi talks about the lunar month. But then there's this thing called as Nakshatra. So Nakshatra is something different from Tithi. So that is how I'll say that sidereal and lunar are different, okay? But I'll come to that again later. Okay, so this periodicity, the reason we needed it is because of seasons. Now we see approximately 4 seasons. Well, in Mumbai, I suppose there are 4 seasons.
Before you go to that,
Yeah?
since you mentioned lunar and you're saying 27.3,
Huh.
why did the appearance and disappearance of the yellow disk,
Huh.
which could be the basis of our
Huh.
timeline,
Huh.
shift to that of the white disk?
Oh,
When there's white disk variant.
Yeah, so the reason is actually very simple. So what happens is that you want to have a look at the larger time period. You want to look at the time period of seasons. So the reason we wanted our calendar is so that we can have a look at seasons. Why do we need to know about seasons? Well, if you know when it's gonna rain, you would be able to harvest your crops before that. If you know when it's gonna be autumn, you will be able to store food before that. You would be able to kill some animals, store the meat and things like that. If you know that it's gonna be winter, you would not be mating. You would be mating before winter, so you don't have kids at that time. So these are things which were defined by seasons. But how do you count seasons? You can't count seasons just by the number of days, because at that time people were counting 1, 2, 3, 4 and then many. Beyond 5, there were many cultures which never had any counting procedure. So ancient Babylonians in some 4000 BC had a counting system, but before that counting systems had not been that prevalent. Even if you're looking at ancient Indian civilizations, at most we can say that we can go till 5000 BC. Before that there has been no system of counting, or counting till a large number. So ancient Rome, which is supposedly said to count a lot, even for them counting till 1000 was a huge task. So counting was a very phenomenal thing which humans came up with. I mean, later on we had this whole system of counting decimals and all that. So it became easier to count days. But before that, a lunar cycle or a lunar month, or should I say approximately 12 lunar months were equivalent to one solar cycle. So seasons would start to have the same effect after approximately 12 lunar cycles. So they saw this correlation. And that's why they shifted from a completely solar day to a lunar cycle, 12 lunar cycles. And that's how it evolved. That's why if you look at the ancient calendars, most ancient calendars, the prehistoric ones, they are lunar. Then came out some solar calendars. And then there is like the Indian calendar, it's a lunisolar calendar. Because most of our events, most of our holidays are based on lunar moon sightings. But then we have to follow a solar calendar so that the seasons are in sync. See, in India we have the...
Did you see that further extended relationship between solar and lunar is establishing with the twinkling things?
There is.
Constellations?
There is. Those are the corrections, those are the fine order corrections that we have to do. So yeah, and so then time evolved, we became a more agrarian society. We had to plant crops. In India, we have got the Rabi and Kharif seasons. So these seasons, how do you know when these seasons are? So for that, you need to know when to, what season it is, what month it is, and at what time should I plant my crops. So if I'm planting my crops just after the rains, that's useless. I should I should plant them sometime before the rain so that when the rains are there, I don't have to just water them that much. And these sorts of things were there, these calculations were there, and the ancient sages, they did those calculations. They saw the heavenly bodies, how they're moving, and they were able to make out some models. At that time, they had got no idea that there's Newton's laws of gravity, which is holding which is holding Earth in some place while it's revolving around the sun. They just had some data. They just saw some things periodically, and they were able to make a model based on that. That's what Aryabhatta and all those sages at that time did. That's what Hippocrates and people at that time did. So you have to give them some claps over there because they did something which we now call as numerical approximation towards a problem which we have got no idea about. Okay, so periodicity. So this periodicity, we came to know about this quite some time back, but the major theory came via the work of Copernicus. So before Copernicus, we had the Ptolemaic model of the universe, that the Earth is in the center, which we call as the geocentric model, and everything around is rotating. But then if you look at the motion of planets, then the planets would have to give a retrograde motion. That is, they are moving about in spirals. And then this Galileo, he observed that the planets have got some moons of their own. So those planets, the moons are moving in cycles around those cycles. So those are epicycles, and that became very complicated. And then Copernicus was like, okay, are you all idiots? I mean, you can just say that the sun is in the center, and everything works out. But he never said that this is the theory of the whole solar system or the universe. He just said that this gives better calculations. It's easier. Then so at that time, there was lots of debate in that. Then Tycho Brahe has been there. He did lots of calculations. So there's a story of Tycho Brahe that he once got into a fight and got his nose chopped off. So then, because his nose was not there, and at that time they didn't have any lenses, so Tycho Brahe could remove his fake nose and he could make better observations, because then his eyes would actually have better sync with the whole telescope setting which they had. So he was able to take lots of calculations. For 20 years he took calculation. Kepler came. He took 20 years to make deductions based on those calculations, and he gave the 3 Kepler's laws of motion. The major one is that whenever you have got planets are moving about around a star, and the amount of time it takes is proportional to the area cube, and I mean those sorts of laws which are there, the 3 Kepler's laws of motion. The velocity is more towards the one of the epicycles and things like that. But the major breakthrough came with Newton, Isaac Newton. He, with the fall of an apple, did lots of things. He gave us the law of gravity, but more than that, he gave us a way to put in a mathematical model. So one thing which most people fail to realize is that there's some part which is happening, there's some physics happening, there's some understanding going on, and then there's a mathematical model. At the end of the day, we are trying to put forward a mathematical model towards things that we are observing, so that we can put in some values and get a precise value. So I give you a car, let's say I give you a Maruti Suzuki, and I ask you, okay, how does this car go? You'll say, yeah, it goes nicely, but then I can give you some number, it goes 0 to 100 in this much, this. So those data in the form of numbers are telling you some specification about the car. Now those data is something which you are actually getting after running the car for some time. Similarly over here, if you can actually predict what's going to happen based on some data, you put in some values like g m1 m2 by r square. This is Newton's law of gravity. Says that if I put in the gravitational constant along with 1 mass, second mass, and the distance, I'll be able to get the amount of force. That's a number which you can calculate. And then you can see exactly how things are supposed to move. You can get equations of motion. That was a huge leap, because now we could predict how things are going to work out. But then physics had an impasse, a big impasse, and that big impasse was the 3-body problem. So I have the sun, I have Earth, I have moon, okay? Moon is rotating like this, Earth is rotating like this, along with that moon is also having a rotation about its own axis, and then Earth is revolving around the sun. A simple physics problem. I mean, you know all the variables which are acting over here. So anyone who has done some part in, I suppose in CBSE till 10th we were taught about gravitation. So it's not very difficult to put in the actual values over here. Take it as a homework, try solving this. It's a very, very difficult problem. I mean, it might seem simple, but once you start putting the variables in that, it is extremely difficult. So a general 3-body problem is actually very difficult. And a solar system is not a 3-body problem. So there would be something like a 300 or 400 body problem, not including the asteroid belt. If I include the asteroid belt, it's some 3,000 body problem. So you can't get an exact solution over there. You have to look at.
What complicates 3-body problem? I'm not clear.
So look at 3 general bodies. I have got 3 bodies, okay?
Let's take 3 years.
Yeah, in free motion, okay? So now if you try to look at how it's gonna evolve with time. So the evolution with time creates the problem. You can just look at at that point you can calculate the force body diagram. But now if I had given some initial velocities, some initial relations, so the initial equation would be something. And then you're putting in what's happening at that moment. So at that moment there's some force acting over there. So those forces, how are they going to counteract or act on the already proponent velocities? That is a difficult problem. Okay. So no. So most of these things. Most of these things, if you are looking at them from the point of Lagrangian mechanics, you can actually get differential equations for this. So the differential equations, they become very difficult to solve. In general, what happens is that most of these differential equations, they are something like linear equations. You can actually put in some values and you can look at what's going to interpolate and get a solution. But if this becomes a second order differential equation with some extra coefficients, then what happens is that this gives a chaotic solution. That is, even a small perturbation to the initial solution would just change your whole solution completely. That's just an example. I mean, you can actually think of it like this. I have a pendulum, okay? And I attach another pendulum to that. Do you think it would be easy to know what the motion of this is? If you feel like that, then just try searching chaotic pendulum. Even a micron difference in the initial position will give you completely different trajectories. And micron is not even touching the boundary. You can go to nanometers or even atometers. Even that can give you completely different trajectories. So these things are planetary bodies. Over there, the trajectory change would be much more severe. And that is why Indian mathematicians were praised for a long time, because they were able to predict eclipses very accurately, very, very accurately. Okay, so yeah. So we had this whole thing about Newton's gravity and then how he was able to give the mathematical equation. And then we understood one more thing, that all this seasonal change, it's not because of the moon. Initially, people believed that 12 lunar cycles were giving the seasonal cycle. They came to know via the work of Newton and everyone else, even before that the seasonal cycle is because of sun and the position of Earth with respect to sun. And also that there's no grandma rabbit on moon. Okay? So, the motions of Earth and moon. Now, this is the interesting part. So, motions of Earth and moon. So, anyone would like to give a guess as to what are the motions of Earth and moon? How do they move? Let's talk about what we all know. Yeah. They rotate, yes. Okay, so very simply, if the moon was not rotating, you would always, I mean, you're seeing one part of the moon which is bright, the other part which is dark. Now, this is in such a sync with the revolution that if the moon was not rotating in its axis, then you would never be seeing the dark phase. Or the dark phase would actually be looking, I mean, whenever you look at the moon, you only see one part of the moon, right? So let's just say that that same side was facing you always. That's what you are seeing, right? So if the same side is facing you, so can I actually ask you to volunteer for something? Can you just stand up? Okay. So now I'm going to circle around you, okay? So if I'm going to circle around you, are you seeing my face in the same way? So sun is over there. Let's say that globe is sun. So if it's going to shine on me and you're seeing my same face, then I actually have to move about like this. So I'm also rotating. If you see it, I'm also turning like this. That's why the moon is rotating. So I mean, you can use some very simple calculations to figure out exactly the rate of rotation of moon itself. And it's a very strange coincidence that this rate of rotation and the revolution are almost the same, almost. I mean, there's a difference of a few hours, but that almost same gives us a very weird scenario in which we can never see the dark side of the moon. From Earth, whenever you want to see the dark side of the moon, it would always be out of phase. You would always see that there's no sunlight over there. So we say that the waxing phases of moon. So moon actually comes and goes back like that. So there are some phases of moon, different phases. And those phases actually are what we are trying to understand properly. Okay.
Is that true for other satellites on planets elsewhere also?
Yes, certainly. No, the revolution and rotation almost the same is not true. So our moon is a special case in that. It's a very special case in that. That's what I'm saying. See, not just that. I mean, why do you think? I mean, do you think it's very natural for satellite to cover the whole of the solar disk during eclipse, total eclipse? I suppose other than moon, there's no other satellite which does that. Those are huge coincidences, almost huge coincidences. And even the moon covering the sun, that's not exactly complete. There's a bit of a gap left. You call that the diamond ring structure which forms, okay, just after totality. The diamond ring structure is telling us some other things as well. I can't go into that, that would take too much time, but okay. Okay, So motions of moon. So we know that Earth rotates, and around this rotation of Earth, there's a lunar orbit. And this Earth is also revolving around Sun. So this is the grand idea that we have of how all these heavenly bodies are moving. But what more can we say? That's fine. So I had mentioned this 27.32 days, the sidereal month. So what is a sidereal month? I'll give you all an idea. Okay, it's not supposed to happen. Sorry, something. Some glitches there, I'm sorry. Devu, start. Okay, so let me just talk about that without the video for now. So let's say I'm Moon over here. So can I ask for a volunteer? Young gentleman, would you like to be a volunteer? You just need to stand. Okay. So can I ask for some other volunteer, please? Thank you. So we are just going to talk about this very simple concept of motion compared to actual motion. So there's something that we see. Now all of you have heard about this apparent sight and real sight. So if you are looking at something like, let's just say I dip a coin in water. So when you look at it from the top, you would be seeing something at some height. Is that the real height? No, that's the apparent height. So the real height by the apparent height, that gives you the refractive index. Okay. Similarly, there's a real day and a sidereal day.
Sorry? Real?
And sidereal. So what sidereal means is that we are looking at the frame of reference of something which is more apparent. So sidereal is like the real thing over here. It's opposite actually. So normally what happens is real and apparent are there. So here sidereal is the real one and the real is what we see. So it's something like this. Let's just say you are Earth and I'm Moon, okay? So I'm gonna rotate, I'm gonna revolve around this Earth. Now if I come back to where I started from, this is one revolution, okay? But how do we look at Moon? So there's a sun also involved. So there's this sun, right? Now Earth is not gonna stay constant. Earth's gonna move, right? So Earth can, Earth can revolve around the sun. So while Earth is revolving around the sun and also rotating, there will be an apparent position with respect to sun, which I'll have to take into consideration because the phases of the moon. So Earth is going around and moon is also revolving around that. So we are going to see phases of the moon. And these phases, they would take a longer time than it takes for the moon to just revolve. So my laptop died. Yeah. Google Chrome में खोल दे.
Why Google Chrome? Just open now.
Because it doesn't have
Foxit है ना, चलेगा उसमें.
Foxit presentation नहीं है. Okay. So this whole thing, this revolution is what will give you the phases. That is what we call as the lunar month. But now, if I'm just gonna say that fine, how much time does it take for me to revolve around this? That's gonna be 27.321 days. So this motion of 27.321 days is what you would observe if you were from an outside frame of reference, right? So that is, okay, you can have a seat, thank you. So this is what you actually use when you're making calculations with respect to, how many of you nakshatras? So how many of you have heard of nakshatras? So Indian astrology always has these nakshatras. So these are called the lunar palaces. So how many nakshatras are there? Why do you think there are 27 nakshatras? Exactly. So they're not exactly 27. There can be 27 or 28. The 28th is in every third year. Why? Because of 27.321 days. The 3 to 1, that expansion with 3 years, it adds up. And then again you'll see that it's not exactly perfect. Okay, thank you. So whenever you're saying this 27.321 days, this 3 to 1, if I add 3 of them, that's not going to be equal to 1. So then after a few years, again you'll have to remove one such leap tithi which is coming, leap nakshatra which is coming up. So that's why we say that there are 27 lunar palaces, or there can be 28 in a leap lunar year. So if you look at the Islamic calendar, sometimes the Islamic calendar would have 355 days instead of 354 days. That's a leap month coming in picture. So these leaps which are coming up are because of these approximations. So this 27 which is coming up, it's saying that, okay, if you're looking at the moon, now imagine a totally different scenario. What I do is I say that fine, let's put Earth in picture in a center, and I'm looking at what's happening in the background stars. So the background stars would change. Which stars would change? Sun, the planets. Do you think any of the background stars would change? Maybe a few which are closer by because of parallax shift, but most stars remain fixed. Now, if you look at the orbit of moon with respect to these fixed stars, then it takes only 27.321 days. So this motion of moon with respect to the fixed frame of reference, it's called the sidereal lunar month. Okay, and this is exactly what you require to know how much movement is happening. So the other apparent movement what's happening is that the Earth is going around while it's also rotating, and while so the moon is taking a rotation. But this rotation, it's going to happen with respect to the line of sight, the line joining Earth and Sun, because the phases of the moon are dependent on Sun. So if there's the Sun, here's Earth, let's say moon is revolving. So moon revolves like this, comes back over here. But that's not how it happens, because Earth also rotates. So now it has to go some extra distance. So let's just say moon started from here and Earth is also going like this. Something extra happened for it to get back to the same position. It had to go an extra part. So I started from here, moon was here, moon was pointed like this, and then once I went over here, moon has to point over here to get to the same position, right? Okay, so Rahu Ketu, how many have heard of that? What are Rahu and Ketu? Huh? Nodes. But if you look at the ancient Indian astronomy text, they are called as two grahas. There are two invisible graha. So the word grahan comes from graha. Sorry, I have said graha comes from grahan. And initially graha was never for planets, it was for grahan. But then these two were called planets, and then it expanded to all. So that's how the word graha comes in picture. But why are there two nodes? That's the question. Why is there Rahu and Ketu? Why not something else? I mean, why not more? Maybe 4, 5, 10. So moon's orbit, Earth is rotating, but moon's orbit, it is at an angle of 5 point something degrees, 5.145 degrees with respect to what we call as the ecliptic. That is the plane of orbit of Earth. So I said that the eclipse would make sense whenever you are looking at the line joining Earth and Sun, right? So this line joining Earth and Sun, when moon comes in between, only then can an eclipse happen. Can eclipse happen any time else? But what if moon was revolving like this in an angle? Then it can come in between Earth and Sun, or in this line, only when it intersects this plane where Earth and Sun lie, right? So these 2 points, the nodal points, are called as Rahu and Ketu. So at that time, the ancient Indian scholars had said that these are two grahas which come over there. They eat them up. So the months in which moon can cross this ecliptic plane, they are called as the draconic months. We call them the month of Rahu and Ketu. So I suppose I have the animation here. So can you all see this small moon over here? This is the orbit of moon, and this you can see this is the line or the plane joining Earth and Sun. So this is called the ecliptic. Okay. Now there are two intersections, one here, one here. But if I speed this up, let's say I speed this up, right now it's 2.5 days per second. I'll increase this. Look at this orbit. This orbit is also changing. This orbit is changing while Earth is rotating. And the amount of time it takes for this orbit to change completely is 18.7 years. How long is a Rahu Dasha or a Ketu Dasha? So that's the time it takes for it to actually just turn around once completely. So one of the major difficulties in calculating eclipses is that lunar orbit is not a very stable orbit. It has got lots of perturbations coming in because of the action coming via Sun and Earth. So the orbit is not 1 year or 354 days. It is 18.7 years. Yes. And that is the major reason why you have eclipses coming in different time periods. So you can see that these are the eclipse seasons. So every year you can have eclipse season coming up in some time period. So whenever there's this eclipse period coming in, you can actually see an eclipse, maybe a lunar or a solar eclipse. So this is how it's exactly happening. Yes?
Full eclipse or a partial eclipse?
So full eclipse, partial eclipse can only happen whenever it's coming out in the draconic month. And again, that would have the, that whole time period coming in. But for a total eclipse to happen, it would take a period of, it can happen in either 1 month completely, or it would take 18 years after that. In that region. So regions are also important over here. Okay, so in one region we are talking about. कैसे होगा? हाँ? F8. किससे होगा भाई तू कर? Okay, thank you. So this tilt of 5.145 degrees, that is what is creating this whole picture. See, this tilt is there. Now, if you try to figure out exactly how many of these tilts would make up something close to 360 degrees, okay, how much time would it take to actually do that? So you'll realize that it would come out to be a multiple of something like 18.7. So that's how we calculate these things. Okay. So motions of Earth, this is a much more fundamental question that we need to answer. I had already said that, well, our sun, the main sequence star which is there, so you all see sun. It's a type of star. So our sun is one of the most average stars which you can find around. For all the special things that we tell ourselves, our sun is the most average star around. But then again, it has given us lots of things. But more than that, this plane of ecliptic. So if I am the sun, Earth is revolving around me, this orbit, it's going to be in a plane. That plane is called the ecliptic. Simple enough, right? But the fun fact is, Earth is not revolving just like that. While Earth is revolving, it's also rotating. And it's rotating at an angle, at a tilt. This tilt is 23.5 degrees. For how long will it be 23.5 degrees? For how long has it been 23.5 degrees?
6 months.
Huh? No. It would be 23.5 degrees for longer periods of time. But this tilt changes. I'll come to that as well. But this tilt is the reason why we have seasons. So I suppose all of you know that, right? So at the end, so this is the initial thing which we had, that 1 day is 86,400 seconds. Then the mean solar time is 365.24219 days. What that means is, if sun is there and I start Earth at this point and I go back again, Earth is at exactly this point. So Earth's center is at that point. Doesn't mean Earth is in the same phase. The phase of Earth can change. Okay. So that same point, if we are having that, then yes, that's 1 year. That is 365.24219 days. And yes, the axis is at a tilt of 23.5 degrees, and this creates the seasons. So I want to give you all an idea of what these seasons pertain to. Yes. So in this slide, you all can see Earth here. Okay. And can anyone tell me what is the latitude for Mumbai? 72. Huh? 72. Latitude, not longitude. 19.7 if I'm not wrong, right? So let's put it 19.6. So this is Mumbai's latitude. Okay, and let's put some labels in there. So we've got Tropic of Cancer, Equator, Tropic of Capricorn. So we are closer to Tropic of Cancer. So we are going to have a tropical weather. And let's animate this. So what happens? So while Earth is moving about, you can see how Earth's motion is happening, right? Now there's some numbers which you can see in this background coming up over here. Sun's declination, Sun's right ascension. So let me change the view a bit. So instead of looking at this from Sun center, right now we are at this, we are putting this all with Sun at the center. What if I put Earth at the center, okay? And then I fix the frame of reference. I mean, I use the fixed stars over there in the background. So this is called the celestial sphere. I'll talk about that in more detail. But what celestial sphere means is, I have got Earth, and around Earth, I cover everything with an abstract, with a very huge sphere. And this sphere is going to have all the stars that I can see projected on that. So there are some stars which would remain fixed. Every day Earth rotates inside the celestial sphere, and we can see some fixed stars, some stars which should move. Okay? So in that frame of reference, what happens to Sun is this. Now, mind you, you can actually have a look at this. The days are changing continuously, and for each day, there's a unique position for Sun. Sun has a unique position on the celestial sphere every day. Similarly, if you were looking at a lunar cycle, you would see that each lunar month, each day in the lunar month corresponds to one unique day. The sidereal month, not the real one, the sidereal month. And you can see that as that is happening, you would see different sorts of ways in which sunlight is going to come up over here. Now, if I look at the beam spread, you would see that during the time when it's what we call as summers. So July, this is summers for us, right? So just over the top. And once it starts going till October, November, you'll see that they start coming at an angle. So the beam spread increases, and that creates a colder weather. So this is how exactly seasons are happening. And the only reason is that this angle, 23.5 degrees. So you can see that Sun is going about in this oblique. So this green line which you're seeing, what I'm doing is I'm extending the equator. This other thing, it is at an angle of 23.5 degrees. So if my Earth is rotating like this, Sun would appear to be going from here to here, right? So that angle is 23.5 degrees. So I can tilt my Earth back, and that gives me that the angle of the Earth's axis is at a 23.5 degree tilt. So this whole intersection between them, it's called as the ecliptic belt, and these points of intersection are very important. I said previously that these points, I mean every point over here can correspond to a day. So what will this point correspond to? These points would be uniquely marked whenever we are looking at the motion of Earth and Sun, right? So these points, they have lots of relevance when it comes to astronomical calculations, because these points are when Sun is, okay, let's just look at the date when this happens. So let's just look at the date when this happens. So September 21st, equinox. Which one would this be? March 21st. So these are the equinoxes. So this is the vernal equinox, that's the autumnal equinox. And why is this happening? So if you're looking at the tilt over here, then we are at an angle. What we want is for an equinox, the day and night have to have same, 12 hours. So when this is further away, then the light is following on this at an angle. And the axis, so look at the line joining Sun. So let's say that is Sun. I have a line joining Sun and Earth. So right now the tilt over here is at an angle of some degrees, right? It's not 90 degrees. But if I want everything to be, I mean completely day and night, it has to be like this. Although this angle is here, so now angles are in 3 dimensions. So this angle is here pointing like this, but the angle it's making with this line joining it, it's 90 degrees. So that's exactly the time of equinoxes. So this sorts of, yeah. That's the celestial sphere. That's the celestial equator. So we take the equator of Earth, we extend it on the celestial sphere, that's called the celestial equator.
But that equator is the actual equator on the Earth,
Yeah.
from the view from the sun?
From the Earth. Devu. Okay, thank you. Okay, so this axial tilt seasons are okay. So that gives us a reason why we have to be so concerned about how much time it takes for Earth to complete one revolution, right? So 365.24219 days is important. We want to approximate that as best as we can. And the better we approximate it, the better the years we have. So celestial sphere, I already talked about that. Okay, so as I said that this is happening. Now, how much time does Earth take to complete one revolution, one rotation inside the celestial sphere? Is it the same as 1 day? It isn't. So how far away is it from 1 day? That is the question. And it's got a very nice explanation. So let's do an experiment, okay? And I ask all of you, I request all of you to do this experiment once you go back. Look at the night sky. I mean, Mumbai's night sky is not that nice, but still you can make out a few very clear stars. Just go over there, mark a time, like let's say 9 p.m. I go over there, mark some stars, that's fine. Right now I'm seeing this star on the top. You mark it. There are lots of applications available through which you can exactly see what star it is, okay? You mark the time, and then you wait for 6 minutes. Look at the night sky, okay? Then mark whichever star is on top of you and other stars which you can mark at that time. Come again the next day at exactly 9 p.m. What do you think you'll see? Would you see the same stars? I mean, same star which I had seen previously at 9 p.m.? No. The one which you saw 6 minutes later would be the one which you'll see. So what's happening over here is that although Earth is rotating, along with that it's also revolving. So while it's revolving, at that time all the things in the background, they keep on shifting. So zodiac, sun sign, which month's, what is this month's sun sign? Capricorn. Why is Capricorn the sun sign? Because that is the one constellation which is which is behind sun. But can you normally see Capricorn? At other months you can see Capricorn. Now can you see Capricorn at any moment, from any point on Earth? No. So the night sky, as you're seeing it, keeps on changing. And this change takes a period of exactly 1 year. 1 year plus that extra day. So while Earth is rotating, so there's this whole movie, 80 Days Around the Earth, something, right? So they complete the revolution in one of those, in the east to west direction. And because of that, they gain 1 day. Similarly, if you're going around, if you're looking at Earth and Earth revolving, it gains 1 day. So you have to distribute this 1 day properly. So if you remove that 1 day's part, so 1 day divided by 365.24219, you'll get a number. So that amount of time you have to remove from all the days. And that is exactly something like 4 minutes something, 4 minutes minus 4 seconds. So some 3 minutes, 56 seconds. That's the amount of time which has to be removed from every day. And that amounts to one sidereal day. So this 0.9342, you can calculate 9, yeah?
Why do you say Capricorn you cannot see?
So what is the sun sign?
Yeah, it's Capricorn.
Yeah. So whatever is the sun sign means that sun is standing in front of that constellation. Sun is standing in front of that zodiac. So I'll come to that again. That is also part of this. Okay, I think we can take a break for now. It's 12. Tea is here? Okay, so we'll take a break here. But before the break, let's just get a few things clear. What is one solar year? That is the amount of time it takes sun to make one whole circle in the celestial sphere. Okay? The reason why we're talking about celestial sphere is this. What is one lunar month? The amount of time it takes for moon to complete one rotation in the celestial sphere. And any position of sun on the celestial sphere corresponds to a unique day in the solar year. And any position of moon on this celestial sphere corresponds to one unique day in the lunar month. So take that idea in mind and then try to imagine how we are going to approximate a year by basing the position of sun. Okay? Let's take a break here. And then we'll come to zodiacs.
How do you know with the Earth in the center, you put the green line superimposing the celestial sphere, no? How do you know where is the equator on the Earth?
Oh, we don't.
So So how did you make it?
So that's an abstract construct. That's a completely abstract construction that we are doing just so we can get better calculations done.
But you could have done it anywhere else.
Yes, we could. We could. We can absolutely choose any other reference. But why are we choosing the equator? Is because equator is the line which is coming out perpendicular to this axis. So we have got Earth's axis around which it's rotating.
The Earth doesn't know, no?
The Earth doesn't know, but we know. So what we know is that Earth is rotating, right? So what we have done is that we have tried to look at the geometric center of this Earth. So Earth is not a sphere. Let's get that fact clear. Earth is not a sphere. The best way to describe Earth is an oblate spheroid. Okay? But we try to look at a geometric center for this Earth. So we put it somewhere in the center. And then what's happening is that Earth's got an axis. I mean, it's moving about from west to east, right? That's a fact which I suppose everyone knows. So this west to east movement, it's giving you an axis. Okay? Now I look at the plane which is perpendicular to this axis. Okay? And it's passing through the center. Now when you look at this plane passing through the whole celestial sphere, that would give you the celestial equator. If you're looking at Earth, that would give you the equator. So I can show you an animation for that. So I've got lots of animations. There were a few more on my laptop, but it died. I'm sorry. So see this. This is how the celestial sphere is formed. Yeah, sorry.
The celestial sphere is the Copernicus model, right?
The celestial sphere is just a plain abstract construct for doing computation. Yes. It's not a Copernicus model. It's a Ptolemaic model if you want to call it.
Okay, yeah, sorry. Yeah.
So this is exactly how it is. I mean, we are just trying to put forward a few things. So let's play it again. You can see this point over here, right? So this point is the vernal equinox. This is vernal equinox. So there are two equinoxes, the one on 21st of March, the one on 21st of September. So the vernal equinox being on this position gives us an origin point. So now whenever so let's just say I have got a star. So if I'm going to move a star, you can see that there are two types of motion. Now whenever you're looking at a star, the star, when you're looking at it from Earth, it would appear to move around the North Pole, right? Go look at any star in the night sky, they would all appear to be at a radial distance from the North Pole and they're rotating around as the night sky keeps on changing. That's exactly what's happening in the night sky. So if I wake up today, I go and look at the sun appears to be moving. How does it move? It moves from east to west. You can say that it's centered either at the South Pole or at the North Pole. So it's appearing to move about that pole, right? So this movement about the Polaris or the pole point that we put over there, where the North Pole or this axis goes and intersects the celestial sphere, we are calling that point something. So right now we say that pole star is Polaris. But if you're looking at the exact celestial north, I mean that point which is the intersection of the axis and that, it's a bit far away from the celestial, I mean it's a bit far away from Polaris. It's not exactly at Polaris, it's somewhat different from Polaris. This would keep on changing, I'll talk about that as well. But this system, this is called the RA-DEC system, right ascension and declination. So if you look at this, the star would keep on changing its position. So this RA and DEC, which you're seeing over here, RA is right ascension, DEC, DEC is declination. So if that is my north, Polaris, okay, then this is my declination and right ascension is movement like this in a circle. So on a sphere, you're putting a radial geometry, you're putting a radius and then you're rotating about a fixed point. Because Earth is rotating, so this rotating frame of reference makes much more sense. Because now what I can do is that this RA and DEC, there are some fixed points. There are some stars which are fixed. Like as I said, if there was a star where the celestial north is pointing, that would have been a fixed point, that would not change. And there's some other stars in the background which are very far away, which would not shift because of parallax effects. So when Earth is at one point with respect to Sun and another point, so you can actually have a parallax shift in stars if they're nearby. So this parallax shift, the stars need to be at a distance of at most a few light years, not more than that. If it's anything beyond some 50 light years, parallax shift would be much small to be observed by our telescopes. Naked eye viewing, anyways, we can just leave it out. So parallax shift becomes apparent over there, but if you're looking at very far away objects, they would not shift in the celestial sphere. So you can exactly fix the position using RA and DEC. So the only problem was fixing a reference point, fixing a zero over there. So this vernal equinox gives us the reference point that, okay, you start from there. So if you look at this right ascension, the right ascension would be 0 whenever I come to this. And how much time does it take for Earth to rotate? 24 hours. This whole thing is exactly 24 hours. And this 24 hours also refers to the 24 hours which are gained while Earth is rotating once around the axis of the Sun. So if you're looking at the axis of Sun over here, Sun would also be rotating in this ecliptic, as I had shown in the previous video. Okay? Okay. We can start, right? It's already started. Yes. And that's, so you will have to answer that later on when I ask. There's some, I mean, you have answered a question which I have not yet asked, but okay. Okay, so coming to zodiacs and ecliptic. Yeah, he's looking in the future. He's got a time machine. Okay, so zodiacs and ecliptic. So zodiacs, how many of you know what's the zodiac of, I mean, we all are assigned one zodiac in Hindu Kundali, okay? That, okay, you have this zodiac, you have this star sign, this is this month's sun symbol. What does all that mean?
Celestial equilibrium. From the sun, from the Earth, the sun appears to be in the backdrop of those constellations.
Okay, okay. So I'll give you all some more information about that. So I have got Earth and I have got Sun. Now Earth is gonna just revolve around the Sun. So if Earth is here, will I be able to see what's behind Sun? No. Okay. If Earth is here, will I be able to see what's behind Sun? No. But if Earth revolves all around and goes behind Sun, over in that position. Can I see what was behind Sun? Yes. But now what was here would get out, blocked, right? Because Sun is so bright that everything that it covers gets blocked away. Something like 30 degrees around it are blocked away completely. So bright. So this whole region, what we do is that there's this plane, there's the ecliptic belt as we call it. So there's Sun and this Earth. Earth is revolving around the Sun. So we have this plane over here. Now in this plane there are lots of different constellations around. So what we do is we take a 30-degree band over here in this plane. This band is what we call as the ecliptic. Now this 30 degrees is a very magical number. Why? Because if you are looking at Sun, other planets also orbit around Sun, right? And all their orbits can have a tilt. So we try to fix a mean axis, a mean plane over there, which we call as the ecliptic plane. It is not our plane, it's the mean ecliptic plane. It is 1 degree away from our ecliptic plane. And almost, so Jupiter is at an angle of 3 degrees from this, Saturn is at 4 degrees, and Venus is at somewhere around 7, if I'm not wrong. I mean, all of these, they fall under 7 degrees in this ecliptic plane. So they're not deviating a lot. So if you look at the solar system from a wide view, you would actually see that all of them are almost in a plane. And this plane is the ecliptic belt. But this gives us another way to look at things, because now all the planets, they would appear in a plane. So they all appear to pass through this belt, this ecliptic belt. So this is an observation which people at that time made, that Sun, Moon, planets, they all pass through this belt. Every time whenever they are moving about, you will always see them inside this belt itself, this ecliptic belt. But what more? So they tried to find a way so that the seasons, the lunar months, could correspond with something over there. So they found out that there are 12 different, very distinct constellations, which the Greek at that time referred to the zodiacs. Capricorn, Pisces, and all those plethora of 12 constellations. So all these constellations, they are given an area of 30 degrees. So there are 360 degrees, 30 degrees to each constellation. So whichever constellation Sun lies in front of, that's the constellation for the month. Right now, Sun is in front of Capricorn, so it's the month of Capricorn. Then it would go to Pisces, then it would be the month of Pisces. So I'll show you an animation. Told you I've got lots of animations. So can you all see this? So right now, it's the month of January. So let's rotate this a bit. So can you all see this Capricorn coming in? So before this, what was it? December, Sagittarius. Then from Sagittarius, we are going to Capricornus. Earth is rotating while Sun is moving about. So right now, Sun is in front of Capricornus, so it would be Capricorn. Then once we go to Feb end, we'll go towards Aquarius. Somewhere around Feb 22nd, we'll be at Aquarius. Then from Aquarius, we'll go to Pisces. Pisces to Aries, Taurus, and like that we'll keep on rotating. So this whole cycle where we are moving about in the ecliptic belt, the Sun appears to be moving about in the ecliptic belt, that is the solar cycle. And we have divided the solar cycle into 12 parts, 30 degrees each, and each of these 30 degrees, so it makes a square of 30 cross 30. Because there's 30 degrees for each, and then we are taking a 30 degree belt, 30 degree belt, that gives us the ecliptic belt.
Were these created at the time when it was assumed that everything revolves around the Earth?
No, so Greeks, so at that time they had an idea of things, okay, that period is the same. It is that period, it is that period. So it is that period itself, that's Ptolemy's period. So yes, at that time they believed that everything is revolving around Earth. But still at that time these names were given because of the zodiacs at that time itself. Yeah, so they were thinking that okay, everything is revolving around the Sun. So even these constellations are revolving, everything is revolving around Earth. Even these constellations are revolving around Earth, and Sun appears to be in front of some constellation. The constellation is going to affect how things are happening. So that was the idea at that time.
And also, would it depend on which region you are viewing this from?
Yes.
Or is it in front of the Sun?
No. So no matter which region you are in, Sun would remain in front of one constellation only, right? So this place, okay? So that wall is in the background. Earth is rotating, right? So that's why. So the rotation is making so that whatever is in the background of the sun remains in the background of the sun for all people on Earth. Okay, so yes, so this 20-degree wide on both sides, so almost 40 degrees, and 12 regions of 30 degrees each, and this approximates the motion of sun in 1 month. Now, so in Indian astrology, we are not just putting the position of sun, we are also putting the position of stars, sorry, of planets. So at some point of time, it can happen that मंगल अभी उसमें बैठा हुआ है, मंगल की दशा ये चल रही है, या फिर अभी यहाँ पर yeah, so that's all your Rashi and Kundli thing. I would not go into that. That's not science.
So the on Indian astrology, when they divided according to the, I mean they also had 12 signs.
That is because when Alexander the Great came in India, before that Jyotish was there in India, but Jyotish actually corresponded with knowing the positions of stars. Never had it happened in India that we were trying to predict what's going to happen with that. So we were going to predict when an eclipse is going to happen, because those tithis and those moments are important for us. See, Indian astrology, or should I say, we have had some notion of something being better, some time being better than the other times. Okay, so because of that, we had these time scales where we were marking everything. Okay, this is like what they call now that this. क्या बोलते उसको? In whenever there's a wedding, you have this muhurat. So muhurat is a part of a tithi, something like 48 minutes. So those things we were calculating that fine. So nothing should happen during the time of an eclipse. There were scientific reasons for that. But this whole idea of zodiacs coming in and them exactly resembling the zodiacs of the Western civilization, that is because of Alexander the Great. So he came, and along with that came the idea from Greeks, and then that actually propagated in India. And this happened sometime in the 1st century. 300, sorry. 1st century is another thing, I'm sorry. But there's a difference between the two of ours. So the Indian zodiacs, the Indian horoscopes, they are based on a sidereal year, whereas the Western one is based on a solar year. So the Western one would actually keep on changing with time. I'll come to that. Indian one remains a constant. So Indians did some sort of Indian mathematicians and philosophers tended to be a bit people with more swag, I'll say. And they knew how things worked. So I mean, if you look at the things that they have done, so sidereal day is something which people came to know about after a long time. Aryabhat in his time was able to calculate the value of a sidereal day till 7 decimal places. I mean, think about it. At that time, I mean, he's working in some ADs and BCs. At that time, people are still just thinking about how to live, and he has already calculated the value of how much time it takes for Earth to rotate. And it's not your normal rotation that we are looking at with respect to sun. It was rotation on its own axis. And that's a huge task. You have to take lots of astronomical data for that. And he was able to do that. And that one single man was able to calculate the value of pi, the value of √2, and value of lots of things. And in a single book, Aryabhattam. That's something. Okay, so I suppose all of you now know these facts.
When you're saying that these in the celestial man behind the sun, that's the zodiac that was invisible for that duration. How did those guys at that time? I'm trying to imagine myself standing in Greece, looking at the universe, and saying, okay, that's not visible. So as it appears, you start mapping. How did you start mapping it? I mean, how do you construct a map like this?
Oh, this month I feel like we should tame some cows, some bulls. So this is Taurus. This month we should actually have.
That's the name. It's not even a name. That's the naming.
Yeah.
Okay, that's also a smart thing to do.
Yeah.
But before that, I'm saying, how do you map it?
So if you look at the way the mapping is done, it's completely dependent on the civilization and the culture. Like we now map these mean and all that. हम लोग जो हिंदी में बोलते हैं. So those are things that we actually got from the Greek. We never exactly named them ourselves. Those are just translations. Tula or Vrishab, all those are just translations from there. But the way they did it, I don't know. I mean, some historical reasons would be there. Some ways, like if you look at Orion. Orion was named Orion why? I mean, the story is that, okay, he's supposed to be this guy's kind of.
So that's the hunter concept, right?
Yeah, hunter. So he was supposed to be the lover of Artemis, and then he died while fighting this Scorpion. So the Scorpion was also put over there. The Scorpion is the constellation that you're seeing, and Orion is put on the other side. So Orion and Scorpion, they're both on diametrically opposite sides, so that they never face each other, so that they never fight. Now, why they're naming them like that, I don't know. I mean, they might have had some historical reasons, but well, ancient Greek.
Great storytellers.
Yeah, great storytellers and great story makers. Can't say anything against them. Okay, main topic. So now here we come to the main topic of our talk, calendars. Anyone recognizes what this is in the background? Yes. It's a Mayan calendar. And no, this is the Mayan calendar. This is the Mayan calendar. Yeah. So this is the one calendar which I suppose almost everyone knows about, because according to this, Earth was supposed to end in 2012. We even had a few movies on that. And I know a few people, I mean, there were news of people committing suicide because of this. So calendars can have effect on people's lives. Okay, it's an important thing to know about. So what we want in a calendar is that our calendars should approximate a solar year or its multiples. And I suppose the reason is very clear to everyone now. Why do we want to approximate a solar year? Because with that we'll be able to predict seasons. The major thing why we need a calendar is to be able to predict seasons. And that's it. There are very few holidays or very few, so reforms are there when we actually want to fix things. Things like equinoxes, they need to be fixed. And if a calendar can fix these dates, we'll be very happy. Very, very happy. Okay, so what is the simplest way in which we can approximate this? 365.24 integer number of days. 365. Egyptians, they did this. So 365 days. This is the Egyptian calendar. So 365 days has occurred in lots of calendars, the Sumerian calendar, the Egyptian calendar, even the Persian calendars. 365 has been an auspicious day in all of them. So for the Egyptians, they had it like they would have 4 seasons, and they would be all coming up to exactly 90 days, and then they would have 5 intercalary days, which are the 5 days of the gods, separately given out. So they never gave out a reason why these coming up, it's just that they matched, and they were happy with that. But do you think the system would be good? How good would the system be? Exactly. So what happened is that by so this would lose one day every 4 years, right? This would lose one day. So over a period of 1460 years, the New Year's had passed through all possible seasons. So they call this a long year cycle. It's called a Surit or something, and this made the whole system obsolete. I mean, the reason for calendar was gone. It was just like, yeah, fine, we have a system, we have got a few months, a few days of gods, but no reason why this should actually correspond with a season. I mean, some reason, maybe if last year your summer was in this time, maybe a year ahead or further away, it would be this year ahead as well. But the correlation was gone. And then came this guy, Julius Caesar, et tu Brutus. Everyone knows of Julius Caesar? Yes. So Veni Vidi Vici. Have you heard of that? I came, I saw, I conquered. So he's the same Julius Caesar. And in 1546 BC, he came up with this idea that, you know what, our calendars are wrong. They're so wrong that we don't know how to actually just predict dates. I mean, you can't even say whether it would be winters or summers some few years later on a certain date. So we need to fix that. So Julius Caesar, he was a dictator. He called all the people who knew some good astronomy over there, and he was like, okay, fine. You are smart people, fix something for me. I mean, I want something which is easier for everyone to remember. So they calculated for a long time, and in a period of some few years, they were able to say that, fine, you know what, make it so that every year is not 365, but 365.25. So at the time of Julius Caesar, they already knew about the Egyptian calendar. So Cleopatra, one of Caesar's wife, she was from Egypt. So at that time, there was lots of influx happening between Egypt and all these places. So Egyptian calendar was known all around. And 365 days was a norm which they had, and which was able to predict things nicely, but not very nicely. So here the question came, how good are our approximations? I mean, are our approximations good enough to be able to stay that way for a length of time? And a length of time means not just a few years, a few thousand years. So Julius Caesar, he came up, I mean, he got this thing in picture, which is 365.25 solar days. Okay, and so the notion, by the way, Julius Caesar was the one who also included the notion of 12 months. when I was a kid, I used to have, I mean, I had this just sudden spark of insight that, so septa, octa, nona, deca. Septa means 7, octa means 8, nona is 9, deca is 10. So September is 7th month, October is 8th month, November is 9th month, December is 10th month. Are we doing something wrong? Yes. So what is it that we are doing wrong? So this thing came up because in the Roman calendar they had 10 months before Julius Caesar. And there were 2 extra months which were like, okay, winter months, no one needs a calendar at that time, stay in your home. So that's how it was. That's exactly how the system was. So they had the extra months in between. So these extra months they put in between. Yes. And those extra months, they came out in the Julian calendar. And the month of July and August. So July is after Julius and August is after Augustus, who was the ruler who came, who came to rule Rome after this, after he took away the chances from Mark Antony. Okay. By the way, the 7-day week, whom do you think started that? That's a question. I won't answer that. Okay, so nice. Julius is very nice and was able to approximate a year very nicely. And almost all of us still now believe that we are following a Julian year, a Julian calendar, which is wrong. We are not following the Julian calendar anymore. The Julian calendar is obsolete. How obsolete is it? So although we are having 365.25 days, still, so this says that we'll have to take 1 year every 4th year, which would have 1 extra day. But do you think that would approximate 365.24219? It's a bit more. How much more? In every 4 centuries, you're gaining 3 years. In every 4 centuries, you'll gain 4 years. You can calculate that. It's not very difficult to calculate. Just try to multiply this number by 400, and then try to multiply 365.24219 by 400, and look at how much the difference is. It's almost close to 3. So what to do? So this was first observed by, okay, here's the wild card coming in. The first people who observed this and wanted to correct this based on astronomy were Christians, because of Christian reasons. So Pope Gregory the 13th, he was the one who was able to, not just him, many of the scholars at that time had recognized that the equinoxes, they are shifting. And by the 15th century, the equinoxes had shifted by 11 days. And the equinoxes are very important for calculation of when Easter Sunday would happen. So Easter Sunday is supposed to happen somewhere, either after the equinox or someplace around that. So they have this whole calculation with that. And if equinoxes kept on shifting, then what would happen is that equinoxes have shifted a lot, and 21st of March would not be an equinox anymore. We can't do that. They couldn't do that. So they made a change. And the change was that after, in 1582, Thursday, 4th of October 1582 of Julian calendar was followed by Friday, 15th October 1852. So this was the only time in which our calendar ever had a leap. Leap in the sense that we actually missed out a few days. So whenever you're looking at any calendar dates, and if you try to look at this specific period, okay, what happened on 13th of October 1582? Error 404, date not found. So this date doesn't exist. So 5th till 14th of October 1582, these dates don't exist. These are the only dates which don't exist. Huh? Yes, it got 11 days behind, that's why we had to remove those days. No, we are not. So now, so after this. So no, if you reshift the reference point, then again it will be Julian year. So now after this correction has been done, equinox again comes at 21st of March. That again happens now. And now we know that yes, equinox always happens on 21st of March. So how do you calculate a leap year in the Gregorian system? So now the equation is 365.2425, right? That's the amount of time that you have for a year. So every 4th year is a leap year as long as the year is not divisible by 100. But if it is divisible by 100, so we need to have a cycle of 400 years, right? So in 400 years we were gaining 3 years, 3 days. So we have to remove 3 days. So if a year is divisible by 100, but not by 400, it's not a leap year. So 1900 would be a leap year in Julian calendar, it's not a leap year in Gregorian calendar. 1800 is not a leap year, 1500 is not a leap year, but 1600 is, 2000 is. That's why there was lots of debate when the year 2000 was there. There was this whole song also, Dekho 2000 Zamana Aa Gaya. So at that time, they had this huge discussion whether 2000 would be a leap year or not, and it was a leap year. But 2100 would not be a leap year. So this is the Gregorian system, and it is quite accurate, pretty accurate. But do you think this does justice to everything? Yes. So in some 3,333 years, you'll have a 1 day gap. Errors would occur. I mean, you cannot perfectly approximate so that expansion which I showed, 365.24219, that is not the perfect expansion. The exact expansion would be 365.242187 something. It's a long expansion, and that is also what we call as a mean solar year. That can also change because the orbit of Earth, it would also keep on changing with time. There's lots of dynamics involved over here. You can't just say that, okay, this is going to be the exact way. So defining something very exactly becomes difficult. You'll have to have some system over here. But what would not change are the stars and some other things. So, okay. Then there's this, the precision of equinoxes. And this actually brings us to how these are going to happen. But okay, let's talk about a few calendars before that. So lunar calendar. Any examples of lunar calendar? Huh? Indian calendar is a lunisolar calendar. It's not a The Islamic calendar is a lunar calendar. The Nepal Sambat is a lunar calendar. So they have got exactly 354 days or 355 if it's a leap year. And what they do is that there are different ways of making a lunar calendar match with a solar calendar. So there's this thing called as a Metonic cycle. So a Metonic cycle corresponds with making it so that it matches with a solar calendar. Now, normally if you're using a lunar and a solar, a Metonic cycle can be of something like 19 years or 33 years. 33 years would give you more accurate answers, 19 years would not give you that accurate things. So Chinese calendars and Indian calendars use a 19-year Metonic cycle. Lunisolar calendars. Okay, my family used to use this a lot. So this Lala Ram Sarup, Ram Narayan, Panchang sort of a thing which comes. So we would have this at our home every year. I mean, in December end, my mom would go and buy this. And this would, if you just look at the back, there would be lots of things mentioned with Tithi and this thing happening, that thing happening, Krishna Paksh, Shukla Paksh, this is the auspicious moment. All those things are mentioned in this. This is a lunisolar calendar. So before, Gregorian and Egyptian and all those were the solar calendars. Then the lunar is the Islamic one, and this is a lunisolar one. So this is a hybrid one. So what we want to do is that we have a lunar year, which is falling short by 11 days. There's 354 days. So adding 11 more would give it 365. So we're still short of somewhat 11 days. So we want to include these 11 days some way so that we can actually make it match up to the solar calendar. So this process is called intercalation. And you all, would know this, that almost all Indian festivals, all Hindu festivals, all Sikh, Jain festivals, they fall through the lunar cycles. Diwali, Holi, Pongal, Baisakhi, all of them are coming because of something happening in the lunar cycle. Eid is working only on the Islamic calendar, even Muharram and things like that. So this is a fact. Muharram would not occur in the same period every year. It keeps on cycling. And over 33 years, it would come back to the same point. No, because it is there. This is the lunar calendar. So this is a lunisolar calendar. Lunisolar calendar and lunar calendar are different. So lunisolar calendar would make it so that you would have a year, it divided into 12 lunar months, but along with that there would be some things extra coming in. So so lunar year being 354, we need these 11 extra days, and that's the intercalation. And so as I said, Chinese calendar, it follows a cycle of 19 years, and they include 7 intercalary months. So 19 into 29.5 plus 7 into 29.5, add that, that is approximately 19 solar years. That is 19 into 365.24219, approximately like that. So this is what it means by 19-year Metonic cycle of 7 intercalary months. So these are some calculations which they did. quite complicated. No one likes this, right? I mean, Chinese people, they can do these things. We'd never like to do that. I mean, Indians tend to be jugadu. That's how I like to call it. So we did a jugaad. So the Indian scholars at that time, they used a very ingenious method. So we had a very, very sound knowledge of how to calculate eclipses and things like that. We had a very sound knowledge of calculating when it would be, sunrise would happen, when sunset would happen, and when the lunar phases would be in which time period. So the Tithi and Nakshatra, these things are calculated by hand and they had been in practice for a long time. So using that knowledge, our intercalary month was an Adhik Masa, as they call it. And how does it happen? So what you do is, you take a year, you take a month. So if any solar month gets, so there are two types of lunisolar calendars in India. One are the Purna month and the other are the Amanth. So Amanth means that it's ending at an Amavasya. The lunar month ends at an Amavasya, at a new moon. And again, it ends at new moon, so it starts at new moon. Similarly, a Purna month ends at a Purnima, a full moon, and starts at a full moon. So if you're following either of them, let's say I'm following the new moon one, a month. So if any solar month has got two a month, that is two lunar ones coming in, two new moons coming in, then the first one which comes in, that's the Adhik Masa. The second one which comes in, that's the normal one. So the first one which comes in, that's the intercalary month. Now, how many times can it happen that I'm having two lunar months in a single solar month? Now, try to put that in the Metonic cycle and it would exactly come out to 7 months in 19 Metonic cycles. But in general, you can say that this can happen over an interval of 2 years, 11 months, 2 years, 10 months, 2 years, 4 months. So the months of Margashish, the month of Asar, and this one more month, these 3 months can never have an Adhik Masa. Others can have, because of these intercalary calculations which are coming up. And that made it easier for even the common people to know when can they have an intercalary month, which would be the Adhik Masa. But this, it doesn't give the complete picture. There's still, so Adhik Masa is also sometimes called the Rakshas Masa or the month of the devil or something like that. So normally no rituals would be done in this period. But that's, well, some previous things to be done. And this says that the average interval cycle would be 2.7 years, which is the same as what the Metonic cycle gives us. The Metonic cycle gives us that in 19 years, there are 7 intercalary months. So what is the time period that you will require? Again, you can calculate. Every 2.7 years. Axial precision. So if I'm looking at the Earth revolving around the Sun, that's a very nice picture. Moon is revolving around our Earth. And we get a very, very nice idea as to how things are going to happen. But if only life was so good. If only life was so good. Life never tends to be so good. So this axis, which is at an angle of 23.5 degrees, it also rotates. This is called as the axial precession. And this precession happens over a period of 25,772 years, approximately. So in 25,772 years, our axis would have tilted like this once. So over 1 year, you would not be able to recognize it. Maybe over a century, yes. Over a century, it gives us almost 1 degree of change. So this change was first observed by the Greek philosopher, okay, I don't remember the name. It was observed in some 46 BC, 46 or 56 BC. So it's quite old. But now if this axis is changing, then the angle that it makes with the ecliptic would also change, right? So the ecliptic plane is like this. And as this changes, are the points where the intersection happening between the celestial equator and the ecliptic plane changing? Yes, they are changing. And this is called as the precession of equinoxes. So just this 14th was Makar Sankranti. What is Makar Sankranti supposed to be? Uttarayan. I was looking for that word, Uttarayan. That is the southernmost sun can go. So during the change of seasons, sun would rise from one place and set in another. But with the seasons, the position changes. So what we observed is that the sun would go towards the south, most south, and then come back. That's called the Uttarayana. So that is the summer solstice, that is the winter solstice. So when was winter solstice? 21st December. So 21st December was the winter solstice. But our Makar Sankranti, which is supposed to be at Uttarayana, is coming out on 14th of January. And every year it happens on 14th of January. Why is this happening? No, it's still 14th. I mean, it would shift in some time, but for now it's 14th. Why is it 14th? I mean, why is it not 21st of December?
No, no, yeah, but that question I have not been able to answer.
So that is the main question. Why is it like that? So what happens is, I mean, this is what people have thought that the Indian, the calendar that we are following is, it's called the Vikram Samvat. Okay, this was designed by, I mean, people say that this was designed by Raja Vikramaditya. So Sinhasan Battisi, Vikram and Betal, he's the same Raja over there. Okay, so lots of stories about him, but the main thing which people never say is that he designed the calendar, and this calendar he might have designed it in 25 CE, 250 CE. So if it was designed in 250 CE, then looking at this axial precision and the way the equinoxes are receding, you would see that at that time, if it was 14 January, then it would take approximately something like 1700 years to come to this point where it has preceded back till 21st of December. So that is how we have seen this axial precision happening. And okay, so axial precision is making the equinoxes recede. Okay, so the equinoxes keep on receding, and initially at some point of time they would have been at 14th of January, but then this 14th of January. But now I said that this tilt is changing, right? So this tilt is going to keep on changing. The axis, it's at a tilt of 23.5 degrees. So that tilt is going to change like that over a period of 25,700 years. So over some 1700 years, it can change a finite amount, and that finite amount actually made it change from. I mean, when this is changing, the point where it intersects the ecliptic would also change. Those points are the equinoxes. So the equinoxes are also shifting. So these equinoxes over a period of 1700 years have shifted by some 20 days. Yes. So this shift also tells us when the calendar might have been made. The calendar might have been made in 250 CE. So we consider it to be circular, and this circular motion actually has been observed over very, very long periods of time, and I'm pretty certain that in human lifespans we would not be able to even experience a part of it. For most of us, Polaris would always remain our pole star in all our lives. But over time scales, what it's been seen is that this is almost circular. But then again, I mean, almost circular things are too perfect. As a mathematician and as someone who has delved into some physics, I'll say that it should not be a perfect circle. Mostly for some reason, nature likes ellipses. Circles are perfect, but ellipses are more preferred. And the other thing is that this axial tilt is because the initial angular momentum which Earth has, it's over there. And then Earth's, Sun is having some gravitational attraction towards Earth. And if it's an angle like this, then this axial tilt would also have some attraction towards the way Sun is applying gravity over there. So this thing would keep on happening. But this is like the first order difference that we are getting in our axis of the Earth. The second order differences as well, which are coming up because of the motion of Moon, nutations. The third order differences as well. So these differences keep on occurring with time, but well, then again, I mean, most of these differences are not things which you can just observe in your lifetime. They occur over longer periods of time. See, the universe is vast, and the timelines of the universe are too vast. They're in millions and billions of years, and we are living in but just a second compared to our hour of the universe. So these equinoxes keep on shifting by 20 minutes each year. Now try to, so if anyone has a calculator over here, you can see 20 into 25772 divided by 365 divided by 24, that would give you 1, approximately 1. So that is 1 year gained in the whole this period. So yes?
That the equinoxes are shifting by 20 minutes each year.
Yes.
So have we shifted very long since it was like, say,
It has been shifting for a long period of time, and it has been shifting for such a long period of time that our Indian calendars got behind a few dates. So 20 minutes would not matter much, right? 20 minutes, your school bus can get late by that much time. But 20 minutes over a period of 1,000 years would be 20,000 minutes. Over a period of, let's say, 25,000 years would be?
so why aren't the dates changing on these maps?
They should. They should. But then it would create mass chaos if I was just to say that, okay, you know what, today is not 14th of March, today it's 15th of March. Today is not 19th of January, today is 20th of January. Would you believe that? No, no. That's why I said this talk. Is it the year 2020? How certain are you that this is the year 2020? So this axial shift which is happening.
Neither the question was clear nor the answer.
So one thing which I'd like to point out, which can be seen with respect to this axial tilt, is the pole star, the north pole that we are putting in picture in the celestial sphere. So if this shifts, right now this axis, if you extend it, it points at Polaris, somewhere close to Polaris. But if this shifts, would it point at some other star? Yes. So there's this story of Dhruv, Dhruv Tara, as we call it in Hindi. And Dhruv was supposed to be the pole star at some point of time, in some 5th century AD, or even before that. But that changed. So Dhruv was included in the Saptarishi, close to that. Parts of Saptarishi, as we call it, the Ursa Major, they are in this whole belt, which would actually be somewhere, I mean, at some point of time, they would be our pole stars. So the next pole star would be Gamma Cephei. And this would happen somewhere in 4000 CE. So in some 2000 more years, your pole star would have shifted from this Polaris to Gamma Cephei. And if you wait for 25,772 years, it would come back again to Polaris. So now, coming back to this story, the forgetful scientist. So the forgetful scientist, how many forgot about him? So can anyone help the forgetful scientist? How will he know? What external calculation can he do to figure out what year it is? Exactly. So if the period was more than 25,000 years, he couldn't have used that. But since the period is 25,000 years, he can look at the pole star. He can look at exactly where the star alignment is. And based on that, we know exactly how it's supposed to happen. I mean, we have an idea that it's supposed to happen in almost like a circle. We have a trajectory made out. And in that trajectory, wherever it is, based on that, we can exactly predict. If you're looking at it till the arc second place, you can figure out even the month and the date.